Marcelo Laca from University of Victoria.
Yes.
We will speak on C-star algebras of submonoids of the Thompson group F.
Thank you. So one more. So thank you for inviting me, and thank you to the organizers of this, especially in putting together this wonderful program, in particular in this conference. So how my espresso, how my running shoes, can I do 20 in 40? Let's see. So this project is originated many years ago. I cannot even remember. I think it was 2017. And originally it was Astro, talking with Rita about Thompson, and I got interested, we looked. Now I changed motivation, and I changed the goals many times, but now we have results. And it is joint work with Astro, Rita, Ian, Rayburn, and Camille. So here's the Thompson group. F. Presentation is an infinite presentation. There are infinitely many generators, x1, x0, x1, etc. And there's one relation that says that xj, xi is equal to xi, x squared plus 1, whenever I is less than j. So the big generator, j bigger than I, jumps over and acquires one more, becomes bigger. So I wrote it here. It's ji, so this xj passes here, becomes j plus 1. That's when you apply the relation this way. That's the red. And the green is when you apply the other way around. The red substitution is triggered by an inversion when j is bigger than I. The green substitution is triggered by a jump of 2 or more. Because to bring this one back, j still has to be bigger than I. So j plus 1 has to be at least 2 bigger than I. So that's the Thompson rule there. The way it's presented here doesn't use inverses, so you can use the same presentation to present a monoid, and that's a Thompson monoid. And initially we were interested in that Thompson monoid. So to decide whether two words are in the alphabet x0, x1, etc., give the same element, you have to produce a chain of substitutions of this kind, either red or green, that goes from one word to the other. And if you can link those two with the chain, that they are the same element in P. I indicate that by the square bracket. So, well, it may be difficult or easy, I don't know, but one thing you can observe right away is that the length of the word doesn't change because the relations are homogeneous. So the length is an invariant of the element of the Thompson group monoid. And the other thing that is not so obvious, but the small one never changed. So x0 is preserved. So the number of x0s in the word is the same. And if there are not x0s, well, the x1s are preserved. So the smallest element of in a word is an invariant of the word. Anyway, so to decide with two words, define the same element, there's a way of reducing the words, and it's called increasing normal form. This is well known. And what it does, it just removes all the inversions. Whenever you have an inversion, you remove it. At the end, you have increasing indices in the word, and that's your normal form. If you want to compare two words, find the increasing index normal form for both of them. If it's the same, the words are equivalent and give you the same element of the monoid P. And as a result of this, because the increasing index works also in F, P embeds in F. So it wasn't clear before. You have two presentations. There's homomorphism from the monoid into the group, but it is actually an injective homomorphism. It is also true that F is right reversible. It's a group of right quotients, TP inverse F. So this extends the normal form from P to F. And if you intersect two right cones or two right ideals, you get another one. So we quasi-lattice sort. In fact, because it is directed by TP inverse being F, it is really a semi-lattice. And because of that, and I'm going to go ahead of myself here and say that I'm going to consider Toeplitz algebras. The products of generators of the Toeplitz algebra can be weak ordered. You can put all the algebras, all the annihilation on one side, and all the creation on the other side. So, and by a theorem that I think John Crispin and I proved, there's a boundary quotient, has a boundary spectrum. It's just one point. So right off the bat, we get that there's an exact sequence that has a Toeplitz algebra. The boundary quotient happens to be the group algebra of F. So anything that we possibly may have wanted to say about the universality of the Toeplitz algebra, things like that, it hits right in the middle of amenability of the Thompson group. So it's a no-go. This is too hard a problem. We need to change the problem. And we need, the problem is that the things work nicely when the monoid has a big boundary. This monoid doesn't have a big boundary. There's only one point in the boundary. So there's no advantage in considering of this algebra, just really considering an extension of the group algebra. Okay, so we decided to go with a few generators. So for each k, you truncate the presentation at k. Same presentation, but now you have to stop when it doesn't make sense. You don't apply the relation anymore. You have a group and a monoid. And the problem is that if you now want to compare words in pk, the increasing form may take you outside pk. For example, this word here is in p4, but when you move this one over to remove this inversion, a 5 appear, which is not in p4. So increasing index doesn't work. You don't have a reduction. You don't know how to solve the word problem in p. You need another way of reducing. And the other way of reducing is, in hindsight, is obvious. You apply only green arrows. You remove jumps. And the lemma which I put here, because something I would improve, is if you take a function mu of alpha defined on words that sums all the indices of the letter, just look at the indices and sum add them up. That word by the lemma has a unique minimizing element. So that function has a unique minimizing element among the equivalence class of a given alpha. So equivalently, the minimizing element has no jumps of 2 or more. So you cannot apply the green arrow anymore. And also equivalent, which is useful for the reaction. If you have a maximal green chain, then it has to terminate in the minimizing element alpha under bar 3. Yeah, and the proof is what I just said. Every substitution decreases the value of mu by 1, but mu has a positive integer value, so that has to terminate. And when it terminates, you have no more jumps, otherwise you can go one more step. And then using induction, you should, so this is a little tricky, maybe it takes half a page, but the only argument that needs, the only thing that needs an argument is really. As it turns out, we discovered that it has been already slightly different forms, slightly different proof that had been considered by the Armand-Tesson in 2019. And only 2 weeks ago, 2 weeks ago, we found out that Bell in 2004 uses something called the anti-normal form, and turns out to be equivalent to that. And he credits that to Guggen's different instead. So this is an idea that has been around, and it is necessitated by the truncations not respecting the increasing in the normal form, which is the usual one. Anyway, so we have now this reduction, and this reduction is useful because it doesn't require higher indices. Those are it may reduce an index, but it doesn't go up. So it happens. The reduction happens within pk. And at the end, alpha under bar p uses the smallest possible sub-index to represent them. So that's why they don't want this one called greedy, because it uses the least generators. One way of looking at it, which turns out to be useful, is that once you have alpha under bar p, it's factorized naturally uniquely into syllables. And the syllables are separated by drops. So here's an example. If I reduce this word by applying 4 times the green arrow, there's a 5 there that jumps back, becomes a 4, jumps back, becomes a 3, jumps back, becomes a 2, and when it reaches, it becomes a 1. So that's this x1 here. Now that's not inverted, that doesn't have a jump anymore. And then this 1, the 3, there's a jump of 2, so the 3 comes back, becomes a 2. Now that's been reduced in staircase form or green reduced form. And you see there's that's a single element, but here's equal, up, 1 up, equal, and then drop. So this one has 3 syllables. And those 3, that kind of syllable representation, decomposition is useful for studying the words in the one. If you wanted to do the red reduction, so increasing index form, you have to go up to 7 with this book. So you wouldn't be in E5 anymore. We need the 7th candidate. Okay, so some properties of PK and FK. FK, same presentation, I repeated it there, but after 1, so as soon as you have 2 generators, it's not right reversible anymore. So, and the example is that the last generator and the first one have no common upper bound. And what happens is that if you have the last generator appear first, you can never move it off because you will need something bigger on the right. So you can never get rid of a first last generator, and that causes the problem. So it is after 3 included, is not right LCM anymore. So in P3, two elements can have many common upper bounds. We'll see that in some of the monoids, however, higher monoids, it can be infinite minimum, not least, but minimum. So I have examples there about this. And also from 3 on, they do not satisfy the independence condition. Here's a failure of independence, if you know what that is. It's a constructible right ideal, intersection of two principles that is equal to the disjoint union of two constructible right ideals. I come back to that because it's just to convince you that I know what I'm talking about. I have an example of it. Anyway, so the idea that we conceive is study F and P by approximating with a truncation. Well, that's short-lived for F because it's a theorem of Hagler-Pompidou-Raga from 2011 that after k equals 4, Fk stabilizes at F. So you already reach your approximation at the fourth step. And that puts problems on the pKs too. Because as a corollary of that theorem, F is the only group in which pK embeds and generates. And the reason for that is that if pK embeds in a group, which it generates, then that group is a quotient of Fk. But Fk is F. But F doesn't have any quotients other than F, and non-abelian quotient. So you're back to F. Now that kills one of the favorite pastimes, which is to prove that something satisfies nice properties, you try to embed it into another amenable group. Well, it's not going to work here because the only group you will be able to embed is F, and that's the question. Oh, by the way, I should have said it is not known whether F is amenable. It won't be known at the answer to the Okay, so that's the introduction to F and P and Fk and Pk. Now, why are we doing this? Well, the idea is to generate monoids or consider monoids that have nice boundary so that, or nice structural ideal structure, so that the monoid gives rise to actions, partial actions, groupoids, semigroup actions that are in some sense amenable, even though the groups in the monoids are not. So we want, in the sense, we want large boundaries or large spaces, compact spaces. So here's a little introduction to that construction. So the idea is very simple, very standard. It's the Toeplitz algebra or the regular representation. So you take a monoid, this is general, take a submonoid of a group, and this is standard orthonormal basis, you left multiply. So this is a left reaction by P, you just multiply on the left by P. And extend that by linearity and continuity using isometry, and that's the left regular representation. And the reduced Toeplitz algebra is generated by those operators on the L2. So, I mean, you know examples, the Toeplitz algebra of the natural numbers is the algebra of the unilateral shift, and by theorem of Coburn has the universal property. The Toeplitz algebra of Fn is TON, the Toeplitz extension of Mond's algebra, then again has the universal property. And there's another example I put here to mention something a bit more recent. The AX plus B monoid of a ring of integers in the number field has the same kind of universal representation. Anyway, so in general, and by which I mean when the semigroup doesn't have this quasi-lattice property, one has to deal with alternating products like that. So you can condense all the stars together if they are together, you can multiply them, and you can multiply together all the non-stars. But if you have an alternation between stars and non-stars, you don't understand a priori what the commutation relation. So in principle, you have to deal with all those problems. And beyond the quasi-lattice order, in which case you can put your weak ordering, the non-stars on the left and stars on the right. It's a tough nut to crack, but it has been cracked by Shibley. And he focused on this thing called constructible right ideals. So let me explain by example what they are, so you know how naturally they arise. So let's deal with an example with 4 elements. So it's a LP star and Q and R star LS. That's an operator in L2 of M. When P, Q, R, and S are in M. What is that operator? So you just multiply, because you have the rule for multiplication. You multiply on a basis element, and you come up with, well, the S multiplies, the R wants to divide, but it can only divide when you can divide, and you can divide if Sx in Rm, which is the same thing as saying when X is in S inverse Rm. So here's a gate through which your element has to pass. X has to be in its inverse area. And then suppose that it does, then you continue multiplying, the Q multiplies, that's no problem, but the P wants to divide, but it can only divide if it's already there. So there's another gate, and the other gate is X has to be in its inverse R, Q inverse P. So in order for that multiplication to give you non-zero, you have to pass the two gates, this one, first one, this is the second one, otherwise you get zero. So that's your multiplication. And if you assume further that P inverse Q are inverse S, because that's the multiplication that appears here. Assuming that element is the identity, then you get the same element as you had before, delta X. So in that case, the product that you're after is multiplication by a characteristic function of a set. And that set is the constructible right linear. And all of them are right like that. And the reason we need to consider them is that what is right is to only consider representations that preserve that structure. So here's a general version of it. So constructible right ideals, they you take as a monoid, you look at words, even length, you alternate either alpha dot means the product with inverses alternating, alpha tilde means reverse the word. And if you have any map into a C-star algebra, you form a similar product where instead of inverses, you alternate with stars. So start with a star on the left and end with a non-star on the right. And those T dot alphas are elements, typical elements of your Toeplitz algebra. And it's easy to see that multiplication corresponds to concatenation and adjoining corresponds to reversal. And the constructive right ideas in general are these sets where you stay in N, you pass through one gate, you pass through another gate, you pass through another gate. The last gate is the whole word reversed. So that's how they appear. They're parameterized by these words. And because of this concatenation, they form a semi-lattice under intersection. It's complement. Okay, so what is it? Now that we know constructive right idea, we want to define the universal Toeplitz algebra. And the key idea, as I said, is consider only representations that respect the constructive right ideas. So we have a definition that we came up with, Camila, and it takes it doesn't even assume that the T's, the generators are isometries or partial isometries. We just take elements, and we require that they are determined by the constructive right ideal for neutral words. And this other condition here before, which is the new one we came up with, which is it's not just the lattice, the semi-lattice, it has to be the complemented semi-lattice that is preserved. So if K alpha is the union of K beta, so that when you do the K alpha minus K beta and you take the intersection of that, you get zero, then the similar product has to respect that complementation in the algorithm. So when the semigroup satisfies independence, then you don't need T4, because this already independence reduces to T4 is reduced to T3 by independence. And I should say also that JAG has a more general construction, which is a groupoid using zigzags, which are somehow paraphrasing the constructive right idea. And the word for left cancelled is small categories, and the C-star algebra can be proved to be equal to the one that is presented here. Okay, now this is just to tell you that we have lots of techniques and things that we want to prove, but I don't want you to think too much about this because I'm not going to be able to use it. But the standard argument is the universal maps by the left regular representation to the regular. This is that faithful condition of expectation. The diagonal, because of the condition that Camilo and I chose, are the same. This is always the same. This is the claim that this is the right presentation is that gives you the same diagonal. So it's all hanging. If the universal is equal to the reduced, it hangs on the faithfulness of this conditional expectation, which sometimes we call unique amenability. And it's implied by some of this, by exit approximation, by clarity, etc. And out of that, you get ideal intersection property, or you can say characterization of faithful representations also, and uniqueness theorems, and maybe even ideal structure. Because then if you have a representation of the reduced, then this is faithful. And if your representation is symmetric, so that you have a conditional expectation, then the faithfulness of that representation is characterized by faithfulness of the restriction. So that's the idea of intersection property. Anyway, so here's a proposition that gives you the idea that we're into a little bit complicated situation. If you take only generators, and you decide to take the intersection of principal idea, then, like I said earlier, if you have escape, the last one doesn't give you common upper bounds with anything, because if you have it as first letter, it will stay as the first letter. You cannot put a different first letter. So that's empty. The last two, they intersect kind of nicely. The soup is a product in some sense. But then if you intersect something below, then it opens up. So how does it open up? Well, the intersection of two early generators, that is below k minus 2, is an infinite direct, is an infinite disjoint union of principles. And there are the product of the xi is jxi, but there's also a prefix, and this prefix is complicated. It could be empty, could be just the empty word of identity, but it can also be this complicated. So it's generators from j plus 1 up to k plus 1, and when you put it in staircase form, xk plus 1 is there. The last letter is xk plus 1. So that's a parameterization of the intersection of those two. So you see that each one of these, because they're disjoint, is a minimum lower bound, but none of them is the least number. Anyway, so, okay, so now we thought we were in business because we can handle this, but then it turns out that we forgot something. If we want embeddings of the zeta algebras, it's not just the monoids that have to embed in each other, which they do because of the staircase form. You can prove embeddings, monoids into the monoids, or the monoids into the groups into the groups. But the presentation of the zeta algebra has this other constitution that has constructible right ideal, but it completely goes out the window. And you can see why. If I have two things that have no common upper bound, because their common upper bound is outside my initial chunk, as soon as I move to the next one, well, I regain the common upper bound. So two things that were multiplying to 0 are no longer multiplying to 0. So it's like the opposite of order 0 map. You want to send something that multiplies to 0. Well, that's not going to work. So we scratch our heads for a while, and then we realize, well, we're looking at the wrong embedding. The embedding that we're looking is canonical just because the indices are called what they're called. But really, the embedding has to be smarter than that. It has to preserve constructible right ideas. And we found, of course, there is one in which you kind of preserve the lastness. So if you have the last one in the small one, it has to go to the last one in the next one. So you add 1 in every embedding. So this is a +1 embedding. And the relations are invariant on the adding 1. If I add 1 and add 1 and add 1 and add 1, I get a relation. So it matches the monoid property, but it now preserves the constructible right idea. So this +1 embeddings give you an injective system of monoids. Small detail, the limit is a new monoid. This green thing here, I'll tell you in a second what it is, but it's not P. Fortunately, it's not P. And the embedding goes, take a generator, you go to +1. Each time you go to +1. And because you have embeddings of monoids, that is preserve the idea abstractly, constructible idea abstractly, you have direct system of homomorphisms of universal. All you need is a universal property. So that's fine. But we can verify that those embeddings are faithful on the diagonal. And since the diagonals are the same as the reduced ones, we have a theorem with Camila in our paper about the algebra that says that now it drops down to the reduced. So now we have an injective system at the reduced level. By the way, I should say that we started looking at this problem before we had the definition of Toeplitz algebra that we're applying to approach the problem. And it was coincidental. We were working 2 different things. We didn't know how complicated Thompson monoids were, but we did have an idea that we wanted a definition for Toeplitz algebras that included the complementary similarities so that you can preserve the diagonal. And then they came together in a wonderful way and unexpectedly, because these are an amazing collection of monoids where you really need that T4 condition. You cannot do without the T4. These embeddings of Toeplitz algebras are not easy to come by, but because you have that T4, you verify the diagonal, then you get into it. So you take a limit, and the limit, of course, is the T lambda of this P less than 0. And with P less than 0 is, it's like a negative Thompson. You just put the same relation, but take negative indices. So it's the other side of Thompson. So it's not the positive generators, you just take negative generators. And the difference is not in the relation. The difference is that you have a maximal element, you have a largest index. So you have an index that will never, you have an index that will, okay. You have a larger thing, I don't know. So that monoid generates a group, it embeds in F, and I'm 99% convinced that the group it generates is at least isomorphic to the kernel of the counting zero function. So if you have words that have no zeros, then they generate a group inside Thompson. It's a group generated by this one. Anyway, it's the idea is to say something that is amino or nuclear or unique, and it's close to Thompson, but it doesn't depend on an ability or F. And we're getting close here because this is not quite the Thompson monoid or doesn't generate the Thompson group. It could be that it works. And it does. So we have for k less than 3, you can characterize boundary ideal is compact. K bigger than 4 is strictly larger, but we have a boundary quotient. It is purely infinite simple. And at the very end, we take all the generators because there are infinitely many minimal generators, which are the letters. Then there's a very old result of that says that that's a boundary quotient already. You can't have an idea that simple. So I spared the sketch of the proof, but it is very, very fast because of a characterization of purely infinite simple that Camille and I gave you. Looking at the monoid itself. No, not at the group, but at the monoid itself. It's a combinatorial thing. You can put things in the front. You get purely infinite simple. Okay. So simple, unital, separable. What else do we need? Okay, nuclearity. Nuclearity is a serious business. And for that, we need to get our hands into the structure of the algebra. And to get our hands into the structure, we have to replace what we don't have anymore. That weak ordering, which is not true anymore, it has to be replaced by something. So what we could come up with is a spanning set, which is, it kind of looks like weak ordering, except it has the stars on the right, the non-stars on the left, but it has this thing in the middle. It's like a core, like a scattering core. I don't know what you call it. And it is smaller. It only involves words in the letters 0 up to k minus 2. And but anyway, that's the linear span. The closed linear span is the double itself. So this is not easy. Not easy to reduce. This is a little bit. And what turns out is that these core elements here are correspond to constructible right ideas that are not contained in a principle. They're not multiples of a principle. They're sitting underneath the principle. There are many of them. It is kind of reminiscent to what happens if you have a number field and you look at a class number bigger than 1, and you look at ideas that are prime ideas that are not principal. They also appear in the case of the AX plus B monoid. They also appear in that, but in that case, it's just the length of this thing in the middle is reduced. It's just 2. Here it could be in principle arbitrary length. These L alphas could go very long. The only restriction is that they have no xk minus 1s and no xk's. Those are pushed out. So if you have a star k on the left, you can bring it to the right. And if you have a non-star k on the right, you can bring it to the left. But in the middle, you're going to have this intermediate words. This
What do you mean by even subgroup?
even length. So even length because of our convention, when you write you have star and non-star. So it's always even. It's an even product of stars and non-stars. Okay, so the plan is to use this spanning set to realize the Toeplitz algebra of the K as a sister algebra, Toeplitz algebra of a correspondence and the boundary quotient. So we identify as a algebra of the Toeplitz algebra that it doesn't have x zeros. So this is the image of the previous one through the +1 embedding. So it's a smaller subalgebra of T lambda P pk is really T lambda pk minus 1 plus 1. And then we sandwich it between x0 star on the left and x0. So we conjugate with x0 star and then iterate that until we get a closed subalgebra. We get a smaller subalgebra that is contains the T lambda pk minus 1 plus 1 and is closed under conjugation by x0. They can be characterized in other ways. I have one here that is completely cryptical, but I'll tell you what it does. This says that it's generated by the products corresponding to words whose constructible right ideal is recovered by intersecting with the previous algebra and then generating an ideal. This is not automatic. If you have a constructible right ideal that intersect with the previous algebra, you may lose information and you may not be able to reconstruct. But these words, beta are especially in that they do that. And if you want a spanning set, there's a restriction here to be x0 nested. X0 nested means whenever you find x's, the x0s, there is a star to the left of the left of the unstar. There's always a star first, and then it closes there. You can have many nested of those, but always a star to the left and the unstar to the right. You cannot start your word with an x0. It has to start, every word and every subword has to start with an x0 star. So that is x0 nested complex. But anyway, if you now just form a subspace by multiplying this algebra A on the left and on the right of the generator corresponds to x0, the one that isn't there, then you get a correspondence over A. The A value unit product is the one you expect in T lambda, which is the product of C star A. And the theorem is that there are canonical isomorphisms. The Toeplitz Kunst algebra, Thompson algebra of E is the Toeplitz lambda of pk, and the Kunst quotient is the boundary quotient. So now we have realized T lambda and its boundary quotient as bimodal algebra. And then what we aim to do is to iterate the result of Katsura that says that if A is amino, if A is nuclear, then the T lambda is the T is a nuclear. By the way, I should say that we know from work of Astrid, Rita, Camila, and Lillian, this is the ABCD theorem, that T lambda P2 is nuclear. They constructed, they studied that in 2021 and proved that by very different methods. So we need to do that. And so we define two subalgebras, and I can't tell you how they appear, but they are like the cores without the two endpoints. Look, there are. You just take the inside. You just take the alphas in T lambda, and then the alphas in A. Those are these two subalgebras. The alphas in T lambda are unrestricted, just from 0 to L and 0 to K. And then the theorem is that there's an equivalent that tells you that if you know the previous ones are nuclear, the nuclearity of the next one is the same as nuclearity as a coefficient, which is the same as nuclearity as this much smaller one, which is the same as nuclearity of that very, very much smaller one. So you can pick and choose which one you want to show is nuclear. By default, you try the smallest one. Sometimes it's easy to show the one of those. Well, easy it never is, but it's possible to show the one of those. So that's a characterization of nuclearity in terms of this introduced algebra. And the technique is, well, you look at those infinite decompositions of intersections of constructible right ideals for generators, and they kind of give you a strong operator topology relation. And to realize that, we move to the double dual, which is injective if and only if T lambda of pk is nuclear. And using that, we prove that T lambda of P3 is nuclear. And the reason that is accessible is that when you reduce to those smaller subalgebras, one of them is finite dimensional. And the reason it's finite dimensional is a bit of a fluke. You only have zeros and ones because you're in 3 minus 2 is 1. So you only have zeros and ones. And when you start multiplying 0 star 1, it's nilpotent. After 3 times you get 0. So you get a finite dimensional algebra, nuclear, and then use the theory to prove that all the others will be. Okay. We think we have a proof written down, but perhaps not up. That E lambda of M4 is nuclear. Much harder because these guys are not finite dimensional, they're not abelian, they're very complicated. So you have to do like an infinite process to get to them. But just staying with T3 now, I can show you my limited modesty doesn't allow me to not say this. I want to show you a cool theorem. So here's a cool theorem. It's a uniqueness theorem for T lambda of M3. And it says this. Suppose that you have somewhere isometries in a C-star algebra that satisfy the following relation. And the first one you will identify as this one, as multiplication in the C-star algebra. The second one says that T3 doesn't have anything in common with others. The projection of T3 is orthogonal to every other projection. And it adds that if you have 1 star and 0, that's nilpotent order 3. And then the other ones are a bit harder to interpret. We actually have to assume that one of those products is a partial isometry, something that if you have the presentation in terms of element of the monoid, it's automatic. But here we're giving a presentation in terms of the generators. It's four generators, so it's much harder to get all the properties right. So here we have to actually say this has to be a partial isometry. And then the last one is one of those decompositions of is that failure of independence. The intersection of two right ideals is a sum union, and that causes those two, because that sum decomposition there. If you have that situation, we consider you can verify. Then the map that goes from the left regular to the W gives you a homomorphism of C star alpha. You get out of the left regular, you land in C star of the W's. And we know exactly when that homomorphism is an isomorphism, which is when this projection is non-zero. So that's what happens is that this is at the same time the smallest and largest invariant ideal under some dual factors. And if we instead insist that that is equal to 0, then we get a careful answer. Run out of time. Thank you.
So first, all theorems are cool. But I mean, this is
All theorems are what?
all theorems are cool.
Oh, okay.
Yeah, I mean, this is. Can you go back a couple of slides? Yes. So this CL, can you see this as the? So is there any canonical Gauss action on the circle? Whose invariant subalgebra is this one? Is this one? Because it very much sounds to me, like looks to me like a self-similar proof action kind of thing, where you have, so before you had like monomials of the form L mu, L alpha dot mu beta stuff, or something like this. Yes, these ones. I don't know, this looks to me like the middle term, so the algebra generated by the middle term should somehow be an invariant of some canonical.
I'm not sure I can say no, but I won't say no. Okay, but there are two circle actions that work, and they're related to that thing I said at the beginning. Even for P, it's the same for the PKs. The number of letters is a homomorphism of the into the positive integer, and it generates a circle action on the C star algebra. So the length function gives you. And the number of x zeros also gives you another circle action.
Okay.
But other than those, I don't know any others, and I don't think those will give you a switch point algebra or something.
You do have a conditional expectation.
Sorry?
You do have a conditional expectation for this.
Ah, okay, okay.
So okay, so yeah, these guys are, yeah, there are conditional expectations, but they're not necessarily a circle averages.
Any other questions for Marcelo?
Have you tried to write down the groupoid model? You didn't want to answer it. The thing about this topos algebra with PKs, where they're not finitely aligned, but maybe you can see something by, the unit space. I don't know, it just comes from conceptual.
No,
That's what you want.
but not just because I didn't want to, I don't think I could, or we could, I think it's super complicated, but you mean the unit space is this, the diagonal. Yeah, unit space. And we only got like into the first level, it's, the intersection of the ideas generated by generators. Understand the group model, the diagonal, you have to go deeper than that, have to have intersections of ordinary. Maybe it can be an aspect of it, but do you think you can describe it?
It seems hard to understand really all the categorical ideas, so I think it would be hard. And the S one, especially for k greater than 4, there are too many.
So is this A dependent on the K? Was it done here? Is it? Or is it the same?
Yeah.
But in those injections you have some compatibility for them.
No, the A just works for the bimodule.
Yeah, it depends on the K.
Yeah, it depends on the case. It's a subalgebra of still under PK. So you change K, you need a different. I just didn't want to load everything.
Somehow.
Sorry?
Try in the.
So this theorem. Where is it? This theorem
You said.
requires passing from K to L, but you're sticking with K. You have path from L to L plus 1 until you reach K minus 2, but you have the same thing.
And then I think we should thank Marcelo again.